What the heck?
Tagon.
More like what the Tagon. It was my birthday this weekend, so I'm a little exhausted from debaucherous activities. But I need to make a video. So this video is going to be something that I've wanted to make for a while. Very simple video if you understand derivatives and exponential functions and trigonometric functions. I'm going to prove Euler's formula using calculus in my favorite proof of this fact. And I'm going to do it in this stylish bathrobe. I'm going to use this video as a jumping off point to then finally do what commenters, and the few commenters that I have in my previous videos have asked me to do, which is cover hyperbolic trigonometric functions. But to get there, we need to sort of see the connection between trigonometry and exponents. So if you have the time and are willing to sit through a slightly less refined version of one of my videos, you can watch my last one, which is simply me posting a video from a couple years ago where I had to make a mock lesson for a class I was taking in the summer. And that mock lesson, though not official, still validly covers, properties of exponents and logarithms and their derivatives and whatnot, sort of covering where e comes from as a number, which is the base of the natural logarithm. And I'm going to use that, that's the assumed knowledge, and now we're going to cover how exponents are related to trigonometry through the beautiful world of complex numbers. And we're going to use this video as a jumping off point into the next video in this succession of things where I cover hyperbolic functions. I will do another video where I cover inverse trigonometric functions and their domains and how to graph those, because that can get a little ambiguous, much like I did graphing the regular trigonometric functions quite a while ago now. So, here we go. Let's do it. Hopefully I can stay awake for the whole thing. With my trusty cup of joe at my side, I'm sure that won't be too hard. Quick announcement before we start the video. I have an Instagram page for the channel. It is at whatthehectagon, of course, spelled correctly, unlike my email, right? Hectagon I spelled in the email with an A here when in fact it's an O. Whatthehectagon on Instagram, so this is Instagram. I post channel updates there. I also am doing a lot more reading than I used to now, so I'm posting books that I'm reading that I recommend to people. I have a collection of vinyl records that I like to share. Follow me at whatthehectagon on Instagram. I'd like to point out that one of my best friends, who is very much into Dungeons and Dragons, has a YouTube channel called Marching West. He does like a little podcast about Dungeons and Dragons. He does Dungeons and Dragons all the time through his Discord server. He's very, very into it, and I'm sure he would appreciate a bit of a mention. So if you're into Dungeons & Dragons, visit his YouTube channel, Marching West. He also has an Instagram account, again, at Marching West. Also, this fellow, Bill, and I are starting another YouTube channel. I guess you could call it personal reasons, even though it's just kind of funny. Is called Fredwood Live. On YouTube, we're just called Fredwood. It's an amalgamation of two different things that were sort of important to us in our college days, which are getting farther and farther behind us. So this is, again, YouTube. We have a channel called Fredwood. We're going to do kind of silly, just us riffing off of each other vlogs that we edit together in humorous ways. But we're also going to start doing weekly video game streams on Mixer. And on Mixer, our name is Fredwood Live. So if you want to see two kind of dopey former college students do kind of ridiculous video game streams and also other things that we're going to do on top of that on Mixer, our username is Fredwood Live, so check us out. Likewise, we have a Twitter account to promote it, also at Fredwood Live. So I apologize for all of these different promotions. I figured I'd just start putting these out there. So there's a few that I'd like you to check out if you're interested. Is my Instagram account, whatthehectagon. On YouTube, my buddy Bill's channel, Marching West. It has to do with podcasts and the like relating to Dungeons & Dragons. The Instagram account for channel updates for that channel. Our joint channel, Fredwood, where we're going to be posting stream clips and vlogs that we make, which are not in any way intended to be serious. It's all supposed to be just kind of humorous. We're going to stream on Mixer because that's the only way that we can use the camera that we have on my Xbox One, and we're not about to buy a Kinect to do on Twitch. So Mixer, Fredwood Live, and the Twitter account for that is at Fredwood Live. So if you're interested in any of these things, please give us a follow. I really appreciate it. And now on to the video. Okay, so if we're going to be learning about how to prove Euler's formula, it's probably a good thing that I tell you what Euler's formula actually is. It's very simple. It states that if you raise the number e, which is the base of the natural logarithm, to the power of the square root of -1, I, times some x, right, some number, it could be any number you want, complex or otherwise, that this is equal to the cosine of that number x plus I, the square root of -1, times the sine of that same number x. And x here is in radians, of course. We're pretty much never going to use degrees as an input. And this almost seems completely mysterious in every aspect. How could these two things even possibly be related? Both of these are periodic functions with period of 2 pi each, but they're out of phase of each other by 90 degrees, as well as the fact that this is not anything like that. This is at least in the real numbers, it's a monotonically increasing function that gets infinitely large and arbitrarily small absolute value on the real numbers as a domain. So it seems like you couldn't possibly relate these two things together. What you can immediately derive from it is that because these have to do with rotation and periodicity and are related to the unit circle, raising e to imaginary or complex powers clearly has to have something to do with repetitive rotation in some way, and not exponential growth in the way that we're used to. So before we actually get to proving this, I'd like to sort of explain how this method of writing numbers is actually pretty easily related and seen to be related to complex numbers as a subject. So let's quickly talk about that. If we imagine the complex plane, where this is the real axis and this is the imaginary axis, and we imagine some random complex number, in the xy plane this would be given two coordinates, an x coordinate and a y coordinate, and it would just be labeled a comma b, right? That x, imagine the x coordinate is a and the y coordinate is b. That would be the point, and this would be a on the x coordinate and this would be b as the y coordinate. The complex plane is ever so slightly different. As opposed to assigning two different numbers to this point to give you the position, we simply treat the point on the plane as its own singular number, and it's written as the real part a plus the imaginary part b times I, where I is the square root of -1. As you can see, the real and imaginary axes are orthogonal or perpendicular to each other. They are at right angles, which is sort of where we're going to see the fact that complex numbers can be written as cosine plus I times sine, because those two functions are out of phase of each other by 90 degrees, or pi over 2 radians. And it shouldn't come as a surprise, if you remember things from the unit circle, that we can consider the x part of this as something to do with cosine and the y part of it as something to do with sine. All we have to do is reframe how we're labeling this point, because there's two ways in terms of complex numbers to label this point. And one is to get rid of the two number system and simply label it the number a plus bi, right? A plus bi. This is the single number that is this point. It is unique labeling, and it is the real coordinate plus the imaginary coordinate. And the real part is a, and the imaginary part is b. Remember, the imaginary part of a complex number is simply the number that is being multiplied by I in the term when it's of the form a plus bi. So a is the real part and b is the imaginary part. This is merely one unique way to label the point. Another way, if we say restrict our angle in some way, say between -pi and pi, or 0 and 2 pi, as long as it's one complete turn and no more or no less, what we can do is instead draw you could almost call it a vector, but we're going to call it a radius, from the origin, and label that some number r, and consider the angle off of the real axis in the counterclockwise direction, theta, that the point is. So this point is simultaneously a plus bi, but it can also be considered the ordered pair of radius and angle, right? So it's some distance r from the origin, and it is some angle theta from the positive real axis. You can actually quite easily figure out what r and theta have to be in terms of a and b, because what is this but the horizontal and vertical legs of a right triangle, right? If this length here is a, and this length here is b, we can call it bi, but the absolute value of the length is b, or in this case the modulus. The term modulus is used in complex analysis to refer to the size of the number, or the distance to the origin. And it's not too hard to see that r is equal to the square root of a squared plus b squared, right? That's just distance formula, which is of course the Pythagorean theorem. And the angle theta can be written as the arctangent of b over a. Actually, it would have to be a tan 2, which is a slightly different function that takes into account the different quadrants that your point is in, but for in all intents and purposes, it's essentially the arctangent of a over b, because that's what's going to give the angle. Since we know the two legs of the triangle, we can either use arctangent or arccotangent to get theta. Tangent is just more common, so we go with arctangent. The point of me mentioning this is that what we can do is, when we do the rescaling that we did to introduce the unit circle in trigonometry, the legs of the right triangle became the cosine of theta and the sine of theta, and the hypotenuse was just 1. Which means we can actually write every complex number using this r and this theta as r times the cosine of theta plus I times the sine of theta. And the reason that we can do that is because this part is considering a point somewhere on the unit circle in the complex plane, because it has a real part of cosine of theta, which has to be between -1 and 1, and it has an imaginary part of sine of theta, which again has to be between -1 and 1, which means that this point, whatever theta is going to lie somewhere on the unit circle in the complex plane. And then this multiple r is simply a way of extending the distance to the origin, right? So this puts you somewhere on the unit circle, thus defining the direction you're pointing in, and this is the scalar that tells you the size of the number, essentially. And so all we're going to do is ask ourselves, if we set this equal to e to the ix, like I said before, can we prove that theta is equal to x, and can we prove that r is equal to 1, thus showing that e to the ix is in fact equal to cosine of x plus I times sine of x, because that's what Euler's formula states. So what we're going to do is we're going to prove this using basic calculus, and essentially you have to only just accept that, okay, we can do calculus with complex numbers. There's a few things that go into actually showing that that's true. A couple of preliminaries that you have to show, like complex differentiability, that all limits work the same way, and etc., and that's what the study of complex analysis is for. But for now, we're just going to roll with that, because they do in fact work. The theory has been known for well over 100 years at this point. So we understand that we can just do basic calculus with complex numbers, and things behave exactly how you would expect them to if complex numbers really are just numbers like any other, like the real numbers. So all we're going to do is simply answer the question, can we prove that, since we know that any complex number can be written as the radius or the distance to the origin that the number is, also known as the modulus of the number, if it can be written as that number r times cosine of theta plus I times sine of theta, can we prove that a number, e to the ix, is equal to this thing, this statement, which every complex number is equal to? We know that if we raise e to some power, it has to give a complex number. We know that it has to be equal to this form of something, because this is a way to represent complex numbers. All we have to now prove is r equal to 1, and is x equal to theta? Right? We simply do not know if those two things are true. Those are question marks above the equal sign, by the way. And what if we prove that to be true, then we know that this product r will go away, and that we know that the x input in the exponent here is the same as the angle given by the point as it lies on the unit circle, which is to say that the size of these numbers is always going to be 1. The modulus of these numbers is always going to be 1. It's always going to be distance 1 from the origin. If we can prove that this is in fact equal to cosine of x plus I sine of x, then we have a new way of representing complex numbers in the complex plane. We could say this is the point on the unit circle that is given by the direction in which the point lies away from the positive real axis, and then we would simply multiply by some scalar out front, namely r, or whatever letter you want to use, that represents the distance to the origin. So it's actually a really, really useful way of writing the complex numbers, because it very much allows you to combine them in much, much easier ways, which is not so for functions that are out of phase of each other and already don't combine in very many nice ways. So we'll just do some basic calculus, and we will in fact discover that r is equal to 1 and x is equal to theta, thus proving Euler's formula that states that e to the ix is equal to the cosine of x plus I times the sine of x.